In this chapter, we will dive into convolutional neural networks. But before we do this, let us recap the ANNs from the previous chapter. We have seen that we can configure the neural networks to our own ideas. This includes the number of hidden layers we add to the neural network and the number of neurons for each of those layers. Furthermore, we are able to set different activation functions for those layers and know that we should think about which activation function is needed for the final layer. Like maybe a sigmoid for a binary classification, while a softmax might be better for a multiclass problem. We saw that the learning rate and the optimizer we choose have a significant impact on the model's learning success. And without a suitable loss function, the model will never do any good predictions. Finally, we saw that the number of epochs and the batch size have a significant impact on the time the model learns, and too few epochs might stop the model before it was able to learn enough from the data. Since we just wrote a couple of Python lines to build our models, it is difficult to visualize the model and how it works for the inner eye. So maybe this website helps you to understand the way neural networks are built up and trained. Here you can play around with all kinds of settings that we already know from the chapter about ANNs. We can select what kind of input features we want to provide and see the weights and biases that are applied along the connections. We can also add layers or increase the number of neurons per layer. When we are happy with the architecture, we can click on the play button to see the training progress. As this is a very simple classification problem, the model quickly converges to a minimum. However, the same model will fail if we take a more complex classification problem. So play around and try to find settings that can solve this problem as well. So in this chapter, we want to set up a model to detect ships in radar satellite images, which come from the European Sentinel-1 satellite. The data from that satellite is freely available, so we just downloaded the images from the Copernicus dataspace ecosystem and did a little bit of pre-processing, including calibration and terrain correction. Even though this image is already cropped, it is still too large to serve as training data. For the approach that we are going to implement, we will use small patches of 64 x 64 pixels which show ships. And we will define that those patches that show ships will be the class 1. As the model should be able to distinguish between ships and patches that do not show ships, we also need patches that show something else. And those patches will be labeled with class 0. At the end of this chapter, we want to generate a model that is capable to count and highlight the ships in a larger image. As you can see, this model will not be perfect, but as a first object detection model, this is already very good. And as we already know how to do classifications with an ANN, we could think about using it for this task as well, because the universal approximation theorem states that an ANN with enough hidden layers can solve almost any problem. And even though an ANN cannot deal with the dimensions of an image, we could just flatten the 64 by 64 pixels into a sequence of 4096 values and push this data through the model. Well, in theory, this will absolutely work, and you would probably reach an accuracy of above 90%. So see this as an additional task that you could tackle. But it will be very hard to create a perfect model, because we usually do not have enough training data, and an ANN will never be able to develop something like a comprehension for an image, as we would always have to destroy the dimensionality of the image. So it would be nice to have a network that can use the 2 respectively 3 dimensions of an image to get some kind of understanding for what is depicted. Meaning a network that starts to somehow identify edges of objects and puts those edges together to understand what it is looking at. And this is what convolutional neural networks are doing. But before we deal with CNNs on images, we should understand what convolutions are. This row of numbers represents a sequence of data, just like a flattened image. During a convolution, a kernel, or also called filter, is applied upon the data. And as the data is one-dimensional, the filter matrix is one-dimensional as well. In our case, this matrix has got the values +1, 0, and -1. This filter is then applied upon the first 3 values of the data sequence. If the filter matrix had a length of 4, then the first 4 values would be taken. Then each element of the filter is multiplied by the corresponding value of the data sequence, and the sum is taken, resulting in a 0 for the first position. Then the filter is shifted to the next position and the calculation is done again, resulting in a value of 1 this time. This process is repeated until the filter has been applied to all data. Note that the numbers within the filter stay the same during this process. You might have noticed that the final output of this convolution is smaller than the input data. This is due to the filter, which only returns a single value for each position. So let us take a look at images now. An image consists of rows and columns, and often has got several channels. Just like a normal image taken by a smartphone camera, which has got a red, green and a blue channel. The filter matrix for an image then also needs rows and columns, and is then applied across the image just like it is done with a one-dimensional convolution. When the filter is applied across the whole image, we receive an output image which is smaller than the input image. This is again due to the filter, which just returns a single value per position. But thinking about how a CNN can learn something about an image, the question comes up, what could be the weights in a convolutional neural network? Well, the weights are the values in the filter, so they are the parameters that are trained in a CNN and are adjusted during training. For sure there is the bias as well, but I left it away to keep it simple. Now let us pretend that these are the final values of the filter. This is something like a filter for vertical edges. So within an image that depicts a circle, the network would be able to identify vertical edges. But only vertical edges don't give a lot of information that the image shows a circle. We need to be able to detect more kinds of edges, like horizontal edges or somehow slanted edges. And to do this, we just need more filters that have different weights within the matrix. We can now not only identify vertical edges, but also horizontal or slanted edges. I just used edges as they are easy to visualize. Indeed, a CNN can highlight more than just edges with a filter. There could also be filters that concentrate on the light structure within relative homogeneous objects, or filters that combine different kinds of edges. And just like the weights in ANNs, the weights within the filters are initiated randomly. In Keras, we have different kinds of convolutions. There are conv1D layers, like the ones I showed upon the example with the one-dimensional data. Then there are conv2D layers, those are the ones that we will use for our images. Conv2D layers can also be used if you have several channels, like an RGB image, or like satellite images with even more channels. Conv3D layers are also available in Keras. Those are filters with another dimension, so this is like a filter cube. However, we will not use them in this course. A conv2D layer can have quite a lot of settings, so let us go through the most important ones. First, the filters argument. Here we provide the number of filters for the layer. This is more or less the same as the number of neurons in a dense layer. Then the kernel size. This is the size of the filter. A size of 3 by 3 means that the filter contains 3 by 3 weights, which slide over the image. You can also try out a size of 5, 7 or 9, but a 3 by 3 filter size is usually a good start. The strides define the step size of the filter as it is moved over the image. A stride of 1 means it is moved only one position at a time. Strides of 2 make the filter being applied to every second position, and thus skip a position. This means that the larger the strides, the smaller the output image. And that's where padding comes into play. The padding is intended to counteract the shrinking of the image by placing a border around the image. Under the padding setting same, zeros are placed around the image to artificially enlarge it, which counteracts the downsizing. The combination of a stride of 1 and a padding of same means that the size of the image remains unchanged. Then of course we can specify an activation function for a conv layer as well. but I will not go into detail here as we already discussed activation functions. Then there are a lot of other parameters that we can specify. However, this goes beyond the scope of a basic course. Now I would like to discuss two more types of layers. If the final output of our CNN should be a single value and not an image, we will run into some difficulties. As we know by now, the output of a conv2d layer has got the shape of an image, but we cannot put an image into a dense layer. But we need a dense layer as a final output layer to get a single prediction which states whether the image the model receives is a ship or not. So what we can do is to flatten the image after the last conv2d layer to turn it into the right shape for the dense layer. So the first layer I want to mention is the flatten layer. The second layer is the max pooling. The max pooling simply downsizes the array by taking the maximum value from a given filter size. This max pool filter then moves over the input array and thus downscales it, which can help to reduce the amount of data. Some argue that we could simply use a larger stride to receive a downsizing, but max pooling is still applied in a lot of use cases. Finally, I would like to show you two great websites that visualize the functioning of CNNs very well. The first website visualizes a CNN that has been trained on the famous MNIST digits dataset. We can use this black square in the upper left corner to write a number between 0 and 9 into it. I will try it with the number 3. And now you can see how the convolutional layers are extracting information from the digit I wrote. In the first layer, the digit is still clearly visible, and we see how the filters are highlighting different edges and structures. The next layer is a downsampling layer, which is the max pooling that we just discussed. But then follows the next convolution, and the model starts to aggregate abstract information. After another max pooling, the data gets flattened to be fed into a couple of dense layers, until the final layer gives back 10 outputs, 1 for each number. In this case, the model perfectly predicts the number 3. You can also click on the individual filters to get exact information about the mathematical calculations. The CNN Explainer website is a bit more complex, as it shows a CNN that can work with RGB images. You can again click on the individual convolutions to get information how the kernel is applied. Or click on the activation functions to see how they scale the data. When you click on the output, you see that a flatten layer is used to receive probabilities for the individual classes. Both websites perfectly illustrate how a CNN extracts and aggregates information with each additional layer.